So what I'll be lecturing from today is updated from the version of the Lecture 5 lecture notes that were online last week. I wanted to clarify this briefly. So I don't actually remember what I said out loud. I may have said the wrong thing. So when I say that, so remember, let me reboot in your brain the situation. So again, we have two observers in the plane. They're making measurements in space, but also in time. So they're tagging their measurements with time. We considered the special case where the observers at the initial moment were in the same place and had the same axes, so no relative rotation and no reflection. And then one of the observers, we don't imagine them accelerating to begin a motion. They were already moving at that moment, so there was a relative constant linear motion between the two observers. So at time 0, they're at the same spot. And then the second, either observer, from their own perspective, the other observer is moving. So the other observer then continues that constant linear motion after time 0. That was the setup of last lecture. We agreed that from a Newtonian point of view that both observers, so f was the function which converted between the two observers' measurements. And when we wrote down what we thought that should be from a Newtonian mechanics point of view, it was clear that that function should preserve finite lines, so observers should agree which sets of events represent finite lines. We agreed, it was clear in the Newtonian point of view, they should agree which is the first half of the motion and which is the second half. However, so now we're relaxing that, so we're keeping some of those properties of the sort of Newtonian observers, but being very careful about what we're keeping. So the observers agree on the midpoint decomposition, but they don't necessarily agree on which half is first. Okay? They agree on the midpoint of the motion. They don't agree on which interval was traversed first by the linear motion. Okay, that's not so important for the situation with the observers we discussed, but we want to allow observers actually who are moving in opposite directions in time. That will be something that comes out of the analysis. So let me be clear that when I say preserves midpoint decomposition, what's a midpoint decomposition? It was just a set of a pair of sets of events. I wrote AL and AR that intersected in one place and whose union was the entire set of measurements associated to the finite linear motion. Calling them AL and AR suggests there's an ordering to them, but that's not the case. They're not an ordered pair. It's just a pair of sets with a special property. Okay, so that was one thing I hope I got right last time, but maybe I didn't quite say it correctly. And then the third condition, so preserving the midpoint decomposition was the SR2. That was the sort of physical idea we wanted to encode, and then that was translated into a property of the function by the formula you see in the notes, that it preserves the midpoint. And then I'll just write the equation. Okay, so here Sy was Ftx and S prime Y prime was Ft prime X prime. And another thing I want to change okay, so the final condition, this was just encoding the fact, as I just said, that the observers were at the same place at the origin of time. Last lecture I added additional conditions here. Those additional conditions, how should I put it? So remember in the Euclidean setting we had these observers and the transformations related the two observers, right? That's also true in this case with the linear motions. So the set of allowable transformations, that is the appropriate symmetries, tell you the possible pairs of observers, right? These additional conditions I had here picked out a special kind of pair of observers, namely those that, first of all, agree on their axes at time 0 and which are traveling in the same direction in time. Okay. The full Lorentz group, as I'm going to define it this lecture, actually contains transformations which relate observers moving opposite directions in time. So my original plan was to present, just to pick out that special subgroup which was relevant to the observers that I set up at the beginning of the lecture, but coming to think about giving today's lecture, I think that's actually a more complicated way to proceed because these conditions look like they're kind of important, whereas really they can be discussed at the end and they're picking out a subgroup of the symmetries. Okay, so anyway, so this is just the condition we're taking. I'll discuss those additional conditions at some point later perhaps. Okay, so that's our translation of the postulates of special relativity. The precise physical basis for SR2 prime you might wonder about. I have some comment on that in the notes, a very brief comment. I'll maybe expand on that later, but anyway, this is not a physics class. So if you're curious, I can explain. Okay, so what's the theorem we're going to prove? So C was some fixed positive number. We take P to be this diagonal matrix, and we defined the associated pairing as we've been doing. Okay, so the theorem is that F is an SR conversion if and only if, well, this actually falls out of the analysis, but let's add it here. So F is a bijection, and 1, F is linear, 2, F preserves this pairing. Okay. And 3, well, there was a 3 before, but that was encoding the extra condition in SR4 prime, which I've now dropped. So that's it. Okay, so what's the argument? So there's a few things to do, right? I mean, there's a few ways of setting this up. So if something preserves finite lines, it's not a surprise that it's linear. It's just a matter of how you prove it. There's a few different ways of doing that. I've given some references to other papers that sort of discuss this topic within the context of special relativity in the notes. But we're going to do it using the midpoint decomposition. All right, so F is continuous. So which direction am I proving? I'm proving SR conversion implies 1 and 2. Okay, so I'm assuming I've got some function from R3 to R3 which satisfies those 4 conditions. So first of all, we have to prove it's linear. All right. Well, F is continuous. Actually, that was one of the hypotheses here, right? And it preserves lines and midpoints. Okay, so the first claim I actually done it the other way around in the notes. Oh, yeah, let's do that. Because that's the easy case, let's get rid of it first. Okay, so 1, 2 implies SR conversion. Okay, F is linear, therefore continuous. If it's linear, it clearly preserves finite lines and preserves midpoints, right? Just look at the formula for what SR2 prime says. So we really just have to justify this second condition. But that's precisely what SR3 prime says. So there's really nothing to say. So we simply observe, right, that BW P is by definition, which if you expand it out, so I pair something with itself using this matrix P, then just reading out the matrix, I get this, where this is the usual norm, that is the Euclidean length of x in R2. Okay, so then this formula in SR3 prime is just taking if you work out what that is, it's just the left-hand side of that formula. And then the right-hand side, well, that's just applying f to everything. So that's f of that, using that f is linear. Okay, so those two are equal by hypothesis 2, and moreover, they give the left and right-hand side of that formula, so we're done. Okay, so that was the easy direction. If 1 and 2 are satisfied, then we just read off that, that this thing is an SR conversion. Right, so the other direction involves some more work. Okay, so we're supposing this, and first of all, we've got to prove that it's linear, right? I just sketched out why you would believe that, right? If it preserves finite lines, it's sort of plausible. Okay, so here's the claim. I wanted to make a couple of remarks. First of all, the physics doesn't grab you. I mean, really, this is just a pair of lectures about hyperbolic geometry. Right? If you look at the end of the notes, I'll explain that comment. And it's just a kind of miracle that the first non-Euclidean geometry you write down turns out to be the one that's relevant to describing space-time. Right? So this is really just all about hyperbolic geometry from some point of view. Okay, so I'm going to prove this claim first. So that looks something like linearity, right? So for all for t x prime and t prime, sorry, tx and t prime x prime in R3. I want to prove this. Well, the lambda equals half case is SR2 prime, right? If I put lambda equals a half, that's literally the formula that was written down for preserving midpoints. Okay, so we know it for lambda equals a half. Okay, so what I'm about to write down is just that, well, if we know it for lambda equals a half, then the observers by SR1 prime, well, combining the first two, they agree on the midpoint of the half, which one of them may call first and the other one second, but anyway, they sort of agree on the decomposition of the interval, and by continuity they have to match up. So for lambda equals 1/4, they also agree. Similarly, for lambda equals 3/4, they also agree. And then I can put any power of 2 in the denominator I like, right? Just by iterating the midpoints. So for lambda dyadic, which is just an integer of the number of the form I just described, so i.e. lambda is equal to m on 2 to the n for m and n integers. It follows by iterated midpoints. I'm being a little sketchy here, right? So this is sort of a little bit below the level of detail most of the other proofs in the course I'm going to give are. That's because this is an application rather than developing the theory, okay? But there's an exercise in there, and I encourage you to think it through. It's not difficult, but you'll have to think a few minutes to see exactly what I mean by this. But I think intuitively it's sort of clear that that works. Okay, so it works for all numbers of this form. But think about the interval between 0 and 1. Pick your favorite number, lambda. Well, is it in the first or the second half of the interval? I mean, maybe it's at the midpoint, in which case we're fine, right? We already know it's true for that lambda. If it's in the second half, okay, so let's only worry about the second half now. Is it in the first half or the second half of that? Well, as I've drawn it, it's in the first half. Is it in the second half or the first half of that half? Etc., etc., etc. So what I've just described is a Cauchy sequence converging to lambda, right? Which is purely made up of dyadic numbers. Okay, but f is continuous. So if I have this sequence of lambdas which is converging to, the sequence of dyadic numbers which is converging to my lambda, and it works for all those numbers, and the left and right-hand sides are both continuous with respect to lambda, which they are, well, then the left and right-hand side have to also agree at lambda. That's just what continuity says. So, okay, so we've taken care of this statement for all lambdas between 0 and 1. Well, what good is that? That tells us that f is affine. That's another word for that property. So now we just have to run through a fairly standard argument that if a function is affine and it sends 0 to 0, then it's linear. Maybe you've seen this before. Okay. So we're going to bootstrap ourselves off this property to see that f is linear. And this is clearly implied by linearity. It's actually strong enough. Okay. So claim 1. Okay, so to prove f is linear, I have to prove it preserves sums and that it sends scalar multiplication to scalar multiplication. Let's just do it for lambda. This is clear. I'm just reading off this where the second vector is 0, right? Maybe I'll just say it out loud. This works for any pair of vectors in R3, right? Well, just take the second vector to be 0. Then what have I got? F lambda blah equals lambda f blah. Okay. Okay, by setting t prime x prime to be 0, and don't forget using SR4 prime, right? I've assumed that f sends the 0 vector to the 0 vector, which I just used, right? Because I needed to know that was 0 in order to just look at the first two terms. Okay. So claim 2 preserves sums. By the way, most of these proofs are set up so that we're foreshadowing the basic techniques of inner product spaces. So you'll see the polarization identity in a second. So you'll see in practice all of the basic techniques of inner products, or many of them, just in this special case, right? So that's sort of why I'm running this proof, for example. Okay, so how are we going to prove this? Well, we need to use some number. Clearly our vectors want to be something like v and w, and we want to use some number we take out the front. So we just take lambda to be a half, and we feed in 2 v and 2 w. Okay, so v throughout all this, V and W live in R3. Well, a half is between 0 and 1, so reading off what star says, I'm allowed to take those out the front and get a half F2V plus a half F2W. Did this around the wrong way, didn't I? Oh, that's fine. Okay, so that's from star, and then I use claim 1. Claim 1 says once I've split up the two vectors, I'm allowed to move the half back inside. Right? Okay, so that was F of V plus W. Okay. So what remains, I need to prove the version of claim 1, but where lambda is arbitrary. Maybe that's not what I call claim 3 in the notes. So anyway, let's come back to claim 3. That's what, okay, maybe I'll fix it up. It's claim 4 in the notes, so we need claim 3 first. Okay, so if n is an integer, well, if it's 0, then that's SR4 prime. If it's a positive integer, then I'm just adding up copies of V, and I can just iterate claim 2. So I only have to deal with the case where n is negative. But this is an argument you're familiar with from abelian groups. So that's claim 2, but that's 0, and f of 0 is the 0 vector. So from claim 2, I therefore deduce that f of minus v is minus f of v. All right, so I'm allowed to take negatives out the front, which means that I deduce this identity for all integers, right? Because if n is negative, then think about it as a sum of copies of minus 1, then just take the minus, well, split them up, get a sum of f's of minus v's, and then take all the negative signs out the front, and you're done. Okay. Finally, what about an arbitrary lambda? Well, any lambda I can write as an integer plus a number less than or equal to 1, and then I just use claim 1 and claim 3. Okay, so this was claim 3, and this was claim 1. And then just reassembling that, I get n plus mu, which is lambda fv. Okay, so at the end of all those claims, we've got that f is linear. Okay. Any questions about the first part? All right, so what are we going to do? We've still got to prove this second identity. Now that's not quite what SR3 prime says, right? Because SR3 prime, I mean, look at the way I translated the reverse direction, right? I said from 2 we get SR3 prime, but I actually didn't use all of 2. I only used the version of 2 where the first and second vector were the same, right? So actually that's all that SR3 prime is telling me. So I just have to figure out how to deduce the sort of non-symmetric version from the symmetric version, and that's where the polarization identity comes in. All right, so we want to prove point 2 there. Okay, so V and W are in R3. Okay, as I just said, what SR3 prime tells us is this, if you expand it out. For all V, but the point is that we can write an arbitrary pairing in terms of pairings of symmetric elements. Well, maybe it'll be better if I go the other way. Well, sorry, I think it's actually better to do it this way. Okay, so this is an exercise in the notes. Nothing fancy happened here. If you just expand out the right-hand side, use the fact that the pairing is linear in both variables, then this just falls out. Okay. So that's called the polarization identity. It's a useful trick. Right? So we wrote a non-symmetric pairing in terms of ones that have the same thing in both the second and first position. Okay, but SR4 prime tells me that if I have a pair of vectors which are the same, then I can apply f to both of them and I won't change the value of the pairing. So I could write f of v plus w, f of v plus w, but f is linear, I already established that, so that's fv plus fw, fv plus fw. And similarly, that's fv minus fw, fv minus fw. Okay, by linearity of f. All right, but that is the polarization formula for fv, fw. Okay, so that's it. So SR3 prime gives us this. Polarization identity allows us to deduce the full thing, and that's what we needed to show. Okay, so that's the proof of the theorem. So we've gotten ourselves from this sort of physical intuition about observers through a formalization all the way to a characterization of the relevant symmetries just being those linear transformations. Well, yeah, I didn't say anything about F being a bijection, but I think you can think about that. Okay, so what do I want to say now? Okay, so the appropriate group of symmetries . So the set of all linear transformations with that property, with that particular P, is called the Lorentz group. I mean, it's sort of, if you like, the Lorentz group associated to C. But as you'll explore in the tutorial, I can rescale this without actually changing the class of linear transformations I'm talking about and get rid of the c, so it's just -1. So people often do that. So instead of talking about minus c squared 1, 1, we can just talk about -1, 1, 1. And then we still call it the Lorentz group. Okay, so question. Why is such an F necessarily a bijection? Okay, so I'll leave that as an exercise. All right, so okay, so what I want to do now is go back to the original setting of those two observers in the plane and just fill in these comments I made at the beginning about how, well, F is supposed to be the transformation which relates the measurements of two observers in constant linear motion, relative linear motion. But there's some very strange pairs of observers. Maybe we'll do a strange pair first, which are consistent with this definition. Right, so consider the transformation from R3 to R3 given by this matrix. So what is the condition in terms of matrices that characterizes the Lorentz group? I mean, this looks like a condition I have to check for all V and W. As you're familiar with from our earlier discussions, I can translate, I mean, of SO2, for instance, I can translate that equation quantified over all pairs of vectors to one which is just a matrix equation. So what is the matrix equation in this case? Well, if F is given by a 3 by 3 matrix A, then F is a Lorentz transformation. F is in the Lorentz group, let's say. So what does the left-hand side say? It says FV transpose times P times FW is equal to V transpose PW. So FV transpose is V transpose F transpose, and then read that equation for all V and W. It simply says, replacing F by the matrix A, it says that A transpose P A is equal to P. Okay, so that's the condition on a matrix P, a matrix A, sorry, for it to give rise to a linear transformation which has this property for all V and W. Okay, so now let's discuss some examples of matrices A. Okay, so you just check that if I put that matrix into that equation, I mean, you can do that in your head, that it gives rise to a matrix which is an element of the Lorentz group. So in principle, it describes two observers, right? But those two observers measure time in the other way to each other, right? Because mean, this is just multiplying by -1. This is what observer 2 is writing down, recall, associated to an event, and observer 1 writes down the negative time. Okay? So that seems a bit weird. Okay, so that's a bit of an exotic element of the Lorentz group, but I mean, this is consistent with what we discussed about Euclidean geometry, right? I mean, we discussed rotations and then reflections. This is just the reflection in the time axis. We shouldn't be surprised to discover that it's in this geometry as well. Okay, but here's the more interesting example. So, so there's an example in the notes earlier which deduces that, so if f10 is equal to gamma q, this is the situation I discussed last lecture. So take a generic Lorentz transformation and suppose that you have this situation. So f10 is gamma q. I mean, f10 is something, right? Call it gamma q. So this is an aside. Then you can deduce that it must be the case that, well, first of all, gamma can't be 0. And if we set R to be 1 on gamma q, okay, so from, I mean, what am I using here? I'm using that if I feed in 1, 0 in for V and W, the left and right hand sides agree. If you just work out what that says, it says this, okay? Where I've made this substitution, R is 1 on gamma Q. Okay. And then, well, if you further assume that this R, which you should think of as the relative velocity of the observers, is, so the speed is less than C, then you can deduce just by solving this equation that this gamma factor looks like this. Okay, so this just pops out. I mean, feeding in the space directions doesn't really tell us very much new because in the matrix P we have 1s there, which is what we had in Euclidean geometry as well, right? But if I feed in the first interesting vector, which is 1, 0, which is the time direction, then immediately I get this out, this characterization of this number gamma, which appears in the first position, and it's given by that formula. Okay, so then take this matrix, which sort of R here you should think of as being the norm of that vector R. Then we can write down this matrix. And this is the sort of interesting new element of the Lorentz group, which wasn't in the group of isometries of the plane. This is called a boost. Or if you like, hyperbolic rotation, if we're thinking of this lecture purely in mathematical terms. All right, so you can check just by hand that it works. And this is the case we started with. So the corresponding linear transformation is the desired F12 relating O2 and O1 Okay, so if O2 measures if O1 measures O2 to be moving with relative velocity r, underline, then the transformation F12 that we got wrong in the first lecture, the corrected version is actually this element of the Lorentz group. This is the correct way, that is, the way in which, if you actually did it out in physical reality, the observers would agree on the other measurements, which are written purely in terms of invariance of the Lorentz group. Okay, so this is the new element that we were looking for. Okay. There's some exercises here that get you to work through the notion of a light cone, which is just the equivalent of the sphere in Euclidean geometry. So hyperbolic geometry is about cones and hyperbolas rather than circles or spheres. All right. So let me give one more sort of example of this, or exercise rather. Okay, so let f be the linear transformation. Well, I don't have to say f. So take this A, right? So this is describing the situation, as I said, of two observers in relative constant motion, but with the same direction in time, because this actually is positive, right? Okay, so they're moving in the same direction in time. And if you think about it, at the original time, you can deduce from the shape of this matrix that they had the same axes. They weren't rotated or reflected, right? So this is that particular kind of pair of observers. And take that pair of observers. Okay, so suppose there's a pair of events which looks simultaneous from O2's point of view, right? That's what the first coordinates being equal says. And show, so this is an exercise, as long as the relative velocity is positive, I mean, otherwise they're the same observer, right? And the first coordinates are different, well, two things happen. And this is a significant observation for where we're going next into topological spaces. So A does not measure simultaneous events, right? So what do I mean by that, right? Just apply the matrix A to this transpose and that transpose and observe the first coordinates are not equal. That's all that says. So first of all, O1 won't observe those two events to be simultaneous. Okay, and moreover, right, the position where O2 thinks the first event and second event happens, measure the distance between them in the usual sense, do the transformation, so apply A to those two matrices, and then take the metric distance in R2 between the last two coordinates of those two measurements. That's the distance that O1 thinks is between the events, and they will be different. Okay. All right, so that's just putting an underline under the comment that metric spaces are not the appropriate thing for talking about space, at least in the physical sense. Right? Okay, so that raises the question, what is the appropriate abstraction? It's not metric spaces. Well, there's two layers to that, to the answer to that question. The first is this, right? So definition, Minkowski space is the pair consisting of R3 and this particular pairing for that particular P. Well, I mean, I've only taken two spatial dimensions, but just add an extra one on the diagonal, you get a 4 by 4 matrix. Take that with R4, that's what people usually call Minkowski space, right? There's no real difference between what we've done at this level of analysis and the usual 4-dimensional space and time. Okay, so Minkowski space, we're going to call this pair consisting of, well, R3 in this pairing, but what kind of thing is that? Well, it's what's called a quadratic space. So you're going to explore this in the second tutorial. I won't go into the definition now. So a quadratic space is a vector space together with a bilinear pairing, like that, which is non-degenerate. That's what's behind F being a bijection, by the way. It just says that if you pair a vector with everything else and get 0, that vector must have been 0. Okay. So it's a special kind of bilinear pairing. Such a pair is called a quadratic space. And that is the appropriate, right? I mean, metric spaces weren't appropriate because this was not positive definite, right? We needed P to be positive definite to get a metric. That's not, so we don't. But the larger scope in which that matrix sits is the notion of a quadratic space. Okay, so I said there was two parts to the answer to that question. That's one, so that describes what's called flat space-time, if I took this to be a 4. Well, quadratic spaces, we'll explore this in the tutorial, but we won't go too much further into it. But we'll spend a lot of time talking about the concepts which appear in the following definitions. So, I mean, we're not going to talk about general relativity, but I can write down the definition of space-time in general relativity, and then you'll see why all of the concepts to come are sort of an essential language, at least for that. Right. So space-time in general relativity is a connected, 4-dimensional manifold. Locally isomorphic to Minkowski space. Right, so that's the definition. So what goes in, what do those words mean? Well, the manifold is a special kind of topological space. I mentioned topological spaces in the first lecture. Topological spaces axiomatize the notion of local. Right? So there are no global rulers out in space, even pretend ones like in Newtonian geometry. That's what all of this tells you. You know, without any shadow of a doubt, there's no global rulers. You can't use a global metric. So you can only talk about things locally. That's the consistent way to set up geometry. Topological spaces are how you do that. This is the precise way of expressing what we mean by the word local. That's what this definition captures, full stop. Topological spaces express the concept local, just like metric spaces express the concept distance. And local is better than distance. This is a deeper notion. So topological spaces, that's what goes into this. It's locally isomorphic to Minkowski space, so at every point, the tangent space is actually equipped with a non-degenerate bilinear form of that signature, -1, 1, 1. This word signature will also be explained in the second tutorial. Okay, so, and connected, well, that's another property of topological spaces we'll discuss. Dimension, maybe we won't say too much about. Okay, so this was the local story, and then we need the language of topological spaces to go any further. And, well, after some interlude with function spaces, that's where we're going next. Okay, so I'll stop there, guys.